In this example, I'm going to do Coletta problem 525 about a sprinter whose mass we know, who's running at a constant speed of 10 meters per second in a straight line. Then the sprinter rounds a corner, and we're supposed to find the extra force that the sprinter must exert on the ground in order to round a curve of radius 10.0 meters. I think it's safe to assume that the sprinter stays at that same 10 meters per second while they round the curve. All right, let's start this problem by doing some analysis and planning. See if you can tell yourself the story of this problem and figure out what kind of problem it is. Continue by doing as much analysis as possible. All right, I started by telling myself the story that the sprinter is running along in a straight line, so this is sort of a top view, and then starts rounding this corner and rounds the corner with a curve of radius 10 meters so that while the sprinter is rounding this corner, they're doing a segment of a circle with a radius of 10 meters. And they're going at 10 meters per second along here. Let me put that on the drawing. And their speed is 10 meters per second all along, when the straight part and the curvy part. And then I started drawing a free body diagram of the sprinter, but I didn't totally finish. So I thought, okay, I'll take a side view of the sprinter right at this spot here. So there's the sprinter, and they obviously have their weight going down and their normal force going up. Okay, and then I got to this point and I started thinking, what kind of problem is this? So the sprinter is running along the segment of the circle, so this is probably a circular motion problem. And even though they're going at a steady speed, their velocity is constantly changing, so this sprinter is experiencing an acceleration during the part where they're going the curve. When they're on this straight part, they're not experiencing acceleration because the velocity is constant in direction and magnitude. Here it's constant in magnitude, but constantly changing in direction. And so if this is a circular motion problem, I know the direction of the velocity and acceleration at this point. I'm going to draw those on right now. Take a break and see if you can do that too. So the velocity is tangent to the circle, so it's pointing in this direction here, the direction the runner is moving at that moment, and the acceleration always points in towards the center of the circle when we have uniform circular motion, which is exactly what this is, right? Motion in a circle at a constant velocity. All right. So let me add that to my plan at least. So this is a uniform circular motion problem. So that then helps me a little bit with my free body diagram of the sprinter, right? So I'm looking at the top view of the sprinter here, but in my free body diagram, I've moved to a side view. So I have the weight down, the normal force up, and now that I've realized this is a uniform circular motion problem, I know what the acceleration is. It's the centripetal acceleration, whose equation is v squared over r, and it points to the right. Right, it points inwards towards the inside of the circle. So if this is a cross-sectional side view, so right here, if I've cut along a section right here, then this direction is the inside direction. And so I've just drawn a little arrow to say the acceleration is going inward, and I know its magnitude. Okay, so that actually means there must be something wrong with my free body diagram. Right here I have the normal force countering my weight, so I don't have any acceleration in the y direction, which makes sense. But in the x direction, I have this centripetal acceleration, so my sum of forces in x must point inward. So there better be an inward force, something like this. Now, if we think what would be providing this inward force, it's actually, when I'm rounding a curve, I know to round a curve, I have to push a little bit towards the outside of a circle to start making this turn and continue making the turn, right? And the faster you run around a circle, the harder you feel that you have to push towards the outside of the circle. And that's because you push on the ground outside, and according to Newton's third law, the ground pushes back inwards on you. So this is actually the frictional force of the ground on the runner. So that allows me to figure out my plan, right? Because if this is the same magnitude of the force of the runner on the ground, if I find that frictional force that the friction is pushing the runner inside towards the circle to maintain their circular motion, then I also know the force of the runner on the ground, which that's my goal, right? Find the extra force that the sprinter must exert on the ground in order to round a curve of radius 10 meters. Okay, so here's the overview. We're going to do uniform circular motion to find the frictional force F here in this diagram, which will also be the same magnitude of the force of the runner on the ground, which is our goal. All right, so how do we get this F? There's actually two ways. See if you can decide and continue with this problem. Before I continue with that, I actually realized that we need to maybe interpret the problem a little bit more. What it's asking is to find the extra force the sprinter must exert on the ground in order to round a curve. So This is still the correct goal, but we only want the portion that's helping us round the curve. And what that means is in this straight part, right, the runner has to push against the ground to maintain the forward motion, because there's also a backward force, frictional force, probably from air resistance, keeping the runner from going forward. So besides the free body diagram that we've drawn here that's going inside and outside, we should also probably have a free body diagram going in this way that shows a different frictional force pointing in the direction of motion to keep our net forces zero and maintain the motion of the runner. But that's not what this problem is asking about, so we can just stick with this free body diagram. All right, go ahead and continue and see where you can go with this one. All right, so I've decided that now that I've gotten this far, not only is this a uniform circular motion problem, but it's also a dynamics problem, right? Anytime you have a free body diagram, you probably can start thinking dynamics and use your sum of the forces in X and sum of the forces in Y. Go ahead and see if you can finish the execution. The first thing I do is use the sum of the forces in Y, here, normal force upward and weight downward, to write the sum of the forces in Y equals mass times acceleration in Y. Acceleration in Y is 0, so this side of the equation is just 0. I can solve that for the normal force. I plugged in mg for this weight force here, because that's always the weight of an object on Earth. And then I figured out what the normal force is. At the moment, I don't actually see how that's going to help me, but whenever I see a problem that involves friction, I always like to find the normal force. All right, now I can do my sum of the forces in X. In X, we only have the frictional force pointing to the right, which is positive, and that equals our mass times our acceleration in X, which is the mass times the centripetal acceleration. We just plug in our numbers, and then we can get our answer. Here, I get 700 if I'm careful with my units. I get kilograms, meters per second squared. I recognize that that's a newton, and I get 700 newtons. Now, what I found is this force here, but we already decided that the force that friction pushes on the runner is equal and opposite to the extra force that the runner pushes on the ground. So this is actually our answer, although it points in the opposite direction. But I think this is just asking for the magnitude, so we don't even have to include that, and we can call this our answer. Now, you might remember that I said there were, in fact, two ways to do this, right? And the other one is to, instead of writing centripetal acceleration here, realize that this force is the only inward force, and therefore must be providing the centripetal force to keep the person moving in this circle. Then, right away, you could go to writing this force equals the centripetal, like this. And we have an equation for the centripetal force, and this puts us right back here in this same location. So either you can do your regular dynamics where you realize that you have centripetal acceleration, or you can think directly about uniform circular motion and realize that this frictional force has to be providing the entire centripetal force, and that we have an equation for centripetal force. Either way, you'll get yourself to 700 newtons. If we do our monitoring, we should have 3 significant figures, which you can't tell from this, but we do. We have the right units. And I don't have a lot of intuition for how hard one has to push for going that speed, so I can't really check if this is the right order of magnitude or not. But it doesn't seem either crazily big or crazily small.